Okay, dear students, today we shall have a look at another learning rule, that is delta learning rule. Previously, we have seen Hebbian learning rule, which was an unsupervised learning rule, followed by perceptron learning rule, which was a supervised learning rule, but it could only be used for bipolar or unipolar binary or a discrete neuron or a perceptron. Delta learning rule can be used for a continuous neuron. So it is only valid for continuous activation functions, and again it is can be used in supervised training mode. So that means the teacher's response or the desired response should be known, and again it can use only continuous activation functions, that is your sigmoidal functions. It may be bipolar sigmoid or a unipolar sigmoid. The learning signal for this rule is called as delta. And why it is called as delta? We shall see why the learning signal is called as delta. Now in this case, if at all you see, the learning signal is made up of, usually the learning signal would be made up of, in case of perceptron learning rule, it was made up of di minus oi. This is oi, and here it is made up of di minus oi multiplied by the derivative of oi. So this is oi is nothing but f of net, that is f of wi transpose into x. So here, as you can see, we take the derivative. I have written it in both the forms so that it is clear. That is wi transpose x is nothing but net. So you have to calculate f of net and then find the derivative of f of net, that is f dash of net. So here, as you can see here, these are the weights wi1, wij, win, and these are the inputs as usual. Now see here we have indicated this with a continuous perceptron. And this continuous perceptron, before the continuous perceptron, you will be calculating net. And what is net? Wi transpose into x. So these weights will be multiplied by the inputs and you will be calculating net. After calculating net, you will be calculating f of net, that is at this particular point, and that will be nothing but oi. So as your perceptron learning rule, the learning signal first, you calculate the error signal. And what is the error signal? Error signal is di minus oi. So you get this di minus oi or di minus f net of I, and then you multiply that with f net dash. So you multiply with the derivative of this continuous perceptron. It may be unipolar or it may be bipolar. You already know the derivative formulas of unipolar as well as bipolar continuous sigmoidal functions. So you have to calculate the derivative of those functions. Then you will get your learning signal. And once you get your learning signal, as previously done, you have to multiply by the learning rate and you have to multiply by the input vector to get the weight increment. So as I have already told you, this is f net dash is nothing but the derivative of the activation function. Now, why this learning rule is called as the delta learning rule? So we go next to see how this particular rule, from where we get this rule. So the learning rule is derived from the condition of least square error between oi and di. So what is error? Error is nothing but oi minus di. Error signal is oi minus di, right? So how will you get the least squared error? The least squared error is given by this particular equation. So you take di minus oi the whole square. So and you divide it by 2. That is the equation for the least square error, because it is you take the square of the error. So di minus oi the whole square, this is the equation of least square error. And after getting this least square error, the weight update should be such that the least square error should be minimum. And how to find the minimum of anything, minimum or maximum, you all would have studied the thing. What you do is that you take the derivative. The derivative will give you the minimum or the maximum. So that you all would have studied in applications of derivatives. So this least square error signal, which is given as half of di minus y the whole square, here I have substituted OI as f of wi transpose into x. And then the error gradient vector could be found by differentiating this error function with respect to wi. So with respect to the weight, you have to differentiate the error function. Now when you differentiate the error function, what will you get is that you will be getting this, that is your del E. So del E is nothing but dE upon dwi. So the derivative of E with respect to wi, that will be del E. So whenever you take the derivative of this, what will happen is that this will become, this 2 will be coming here and divide by 2. Then the derivative of the inside function. So what is the inside function? This is the inside function which is there. So derivative of di with respect to weight. Now di is nothing but the desired response. It is constant, so it is 0. And what is the derivative of this? The derivative of this function will be nothing but f dash of wi transpose into x. And because this minus sign is there, this minus sign comes out here. Is that clear? It is still not done. You still have to find the derivative of this inside function. And what is the derivative of this inside function? This is wi transpose. So in the denominator also you have wi. So wi will get cancelled. You will get only x. So this is your simple differentiation. You are differentiating this equation and you get the error gradient vector in this particular form. Now this error gradient has to be minimum. That is, your error should be minimum, and whatever we do, it should be such that the error is minimized. That is, the weight update should be in the negative gradient direction of the error. So as can be seen in this particular graph, this is the way, this is the error gradient vector, that is, it is not E but it is delta E, and this is delta E, this is not just E, and the shape of this particular thing will be somewhat like this. So this is the shape, and this is the shape of the gradient of error. That is, the gradient of the error will take this particular shape. Now the weight has to be, now in which direction? Supposing you are here, supposing your initial weight vector is somewhat here, that is, your initial weight vector is somewhat here, then you have to update the weights in such a way that you are going in the negative gradient direction. So negative gradient direction, meaning gradient is nothing but slope. So here the slope is decreasing. So you have to go in the direction of the slope which is decreasing. So if at all I am here, and if at all I want to decrease the slope, that is, then I have to increase, because I have to go in this particular direction. So the weight has to be increased. If at all I am at this particular point here, and it is said that you have to go in the negative direction of the error gradient, meaning negative, meaning the slope should reduce, that is, this direction it should be. So it should go in this particular direction. So that means the weight vector has to be decreased. So the weight update equation is given as delta wi is equal to minus eta times del E. Now what is del E? Del E is nothing but the error gradient vector, which we have already found out, and we multiply it with a constant, that is eta. Eta is a positive constant, and there is a negative sign, such that every time wherever your weight may be, the weight should be updated such that the next weight will reduce the error gradient. So this error gradient should reduce, and until when you have to go on updating this weights till you reach the bottom at this particular point, and this particular point you will be getting the minimum error, E minimum, and that weight will correspond to W minimum. So you have to do the iterations in the delta learning rule till you get the minimum error. But in the problems which are given to you, you will not be doing that because it may take quite a lot of iterations. Immediately you may not finish this particular problem. So it is said that eta is a positive constant. So it cannot be negative, because if at all it's a negative, then the weight increment will not be in the direction. So eta is a positive constant. So the weight update equation will be nothing but eta. I have substituted this del E in this equation. This negative sign and this negative sign will get cancelled, and I get this. So delta Wi will be nothing but eta di minus oi. This is f net, okay, into x, f net dash, sorry, into x. So this eta, if at all we want to write in the form of, in our form, usually we have taken this as c, that is your learning constant. So here it is eta. So sometimes they may give you eta, sometimes they may give you c. So I have written both the rules. Rest everything is same. Just here it is wi transpose x, which is nothing but net of I. So I have written in the form of net. So the weights in this particular method can be initialized to any values. There is no fixed values. So you can initialize to any values in this particular method. Now this delta learning rule, it parallels the discrete perceptron learning rule. So the way you have the perceptron learning rule for discrete perceptron, that is your bipolar or bipolar binary or unipolar binary perceptron. Similarly, we can have a continuous a rule for continuous perceptron, and this is nothing but the delta learning rule. So that is the reason this rule is also called as continuous perceptron training rule, whereas the previous one which we have studied will be called as discrete perceptron training rule. So this delta learning rule can be generalized for multi-layer networks also, and in that case we call it as the generalized delta learning rule will be used in multi-layer networks, and that time it will be called as error back propagation algorithm, which is commonly known as. So there, that is in unit 2. But I hope you all have got my point why it is called as delta learning rule. It is called as delta learning rule because of this error gradient which is calculated here, which is with the equation del E, and you calculate the del operator of the error gradient. That is the reason it is called as the delta learning rule. So now we shall go and solve a problem on delta learning rule.